is the first of 4 videos or so where we're going to look at specific examples of linear systems and actually go through the process of finding the general solution so that you get enough practice with that. The particular system that I'm going to look at right now, I'm going to write in vector form like this. dy dt equals this matrix. That'll be my matrix A, consisting of the entries 5, 4, 9, and 0, times the vector y, where, as usual, the vector y is two-dimensional and its components are little x and little y. I'm going to write it as a column vector. What's the process? We've talked about that in the videos about linear systems. You need to find, well, equilibria first. Look at the determinant of this matrix. Take the product of the diagonal elements, that's going to be 0, and subtract the product of the off-diagonal elements, that'll be 36. So we'll get a determinant of minus 36, which is non-zero, so the origin is the only equilibrium point. And then you want to find the general solution by finding the eigenvalues and the eigenvectors. If the eigenvalues are distinct real numbers, the corresponding eigenvectors will be linearly independent, and taking a linear combination of those eigenvectors multiplied by e to the corresponding eigenvalue times t will give you the general solution. I'd like to derive the characteristic polynomial whose roots are the eigenvalues in the general case where I don't know the entries of A. And once we get this characteristic polynomial, and in fact the eigenvalues themselves, you can use these formulas as a shortcut anytime that you want to. Though you should always be able to derive it from scratch if you need to. So you don't want to forget how to do this. I'm doing it here in a sense once and for all for these next 3 or 4 or 5 videos. And I'll use this over and over again. I need to find the determinant of a minus lambda I, which will, in terms of the entries, be little a minus lambda in the upper left, b in the upper right, c in the lower left, and d minus lambda in the lower right. That determinant will be a minus lambda times d minus lambda minus the product of b and c. And when simplified, this will become lambda squared minus a plus d times lambda, the a plus d being in parentheses, and then plus the quantity a d minus b c. That's the determinant of a right there, which I'm going to label with a shorthand, just the capital letter D. And this quantity right here, a plus d, is the sum of the elements on the main diagonal of A. That's called the trace of the matrix, A, sometimes denoted by TR of A, but for shorthand I'll call it just capital T. So in terms of the trace, the sum of the elements on the main diagonal of A, and the determinant, the product of the elements on the main diagonal minus the product of the elements on the off diagonal, the characteristic polynomial whose roots are the eigenvalues is this, lambda squared minus the trace times lambda plus the determinant. Setting that equal to 0 and using the quadratic formula is going to result in eigenvalues lambda equal to, be careful here, negative b is positive t, plus or minus the square root of b squared, which is negative t squared, or just t squared, minus 4ac, I'm talking about the quadratic formula here when I talk about a, b, and c. That'll be minus 4 times 1 times d, all over 2a. 2 times 1 is just 2. So your eigenvalues are those two numbers, if they are indeed distinct. Thinking about the case where you've got real eigenvalues, you're going to be in the case where t squared minus 4d is greater than or equal to 0. Which is what's going to happen. Now going back to our original example at the top. Little a is 5, little b is 4, little c is 9, d is 0. The trace is 5, and the determinant is negative 36. Coming back here, that's going to give me a characteristic polynomial of lambda squared minus 5 lambda minus 36. And I can use the quadratic formula to get the roots. This one also can be factored, but I'll go ahead and use the quadratic formula anyway. Let's see, I'm going to get a minus 4 times negative 36. That'll be a plus 144 inside there. 5 plus or minus square root of 169, which is 13 over 2. And so my two eigenvalues are 18 over 2, which is 9, and 5 minus 13 is negative 8 over 2, which is negative 4. One positive, one negative. That's going to end up resulting in what's called a saddle point, which we will see when we draw the phase portrait. I need to go to the eigenvectors now. So consider the positive eigenvalue 9. Find the eigenvectors corresponding to that. I need to replace the lambda in a minus lambda, b, c, and d minus lambda. I need to replace the lambda with a 9, where a, b, and c, and d are the numbers that I had them before. And so what is that going to give me here? 5 minus 9 is negative 4. I'm going to get a resulting system, a homogeneous system with 0 on the right-hand side. So I get a negative 4x from 5 minus 9 in the upper left-hand corner. B is 4, so I have a 4y. And on the right-hand side, I'm going to get 0. C is 9. And D was 0, so I get a 9x plus 9y equals 0 from the second equation. When I first derived how to find the eigenvectors, you might want to go back and look. I talked about the fundamental eigenvalue-eigenvector equation, which looked like this. And we said we were looking for non-trivial solutions to that for V. What kinds of values of lambda give you non-trivial solutions? And if I thought about the original system this way, with lambda equaling 9, it would have looked like this. Let's see. Looks like I made a mistake somewhere. Yeah, my mistake here is that lambda is 9, so this should be a minus sign right here. So I guess it was good that I checked that to see that I made a mistake. And indeed, another way you can check to see that you made a mistake is if you get equations that are not dependent. These equations are multiples of each other. That's what's going to give me non-trivial solutions. If that didn't happen, if I only had one solution to that system, I would have known that I did something wrong. Take either one of those equations and solve for y in terms of x, and you're going to get y equals x. So any non-zero vector whose first component equals the second component is going to be an eigenvector for this eigenvalue. You don't have to bother putting subscripts. I guess I will. I'll label these lambda 1 and v1. Pick the simplest kind of vector that you can think of whose first and second components are equal. Now go to the, and also non-zero. Now go to the other eigenvalue, which is negative 4. Once again, you can think about it either way. I'll think about it in terms of replacing lambda with -4 and considering the corresponding homogeneous system. I don't know if you can hear the squeaking. I don't know what in the world it is. It sounds like somebody who's screaming. There's squeaking in this room. Let's see, we've got 5 is A, minus -4 is going to be 9. B was 4. C is 9. Going back up here, D was 0, minus -4 is going to be +4. And in fact, in this case, you get the same equation in both cases. Solve for y in terms of xa. You're going to get y is -9 x. So whatever x is, multiply that by -9 to get y. If I pick x to be, say, 4, that'll be a nice choice to make because that'll avoid the fractions. Y will have to be 9. So any non-zero multiple of that vector will be an eigenvector for the eigenvalue -4. So my general solution now can be written, capital Y of t is an arbitrary constant. I'll call it k1 times e to the lambda 1 t times v1. I do have distinct eigenvalues here, distinct real eigenvalues. That's going to make these eigenvectors linearly independent, which you can see anyway because they're not multiples of each other. And so that will guarantee that this linear combination is the general solution. K1 e to the 9t times the vector 1, 1 plus k2 e to the -4t times the vector 4, -9. And there are lots of different things that I can do with this. I can leave it like that. I can multiply the scalars times the vectors, and then I can add the resulting vectors. So I can also write it like this, as just one single vector, k1 e to the 9t times 1 plus 4k2 e to the -4t. For the first component, k1 e to the 9t times 1 minus 9k2 e to the -4t. So I can write it like that too. You have the freedom of doing that. By the way, you also have freedom in those eigenvectors. I mentioned that already. If you multiply either of these by a non-zero scalar, you'll get another eigenvector, and you could make those replacements. Well, for example, I could have put a -1, -1 there, and maybe a -8, +18 there. And it still would be the general solution. It would look different, but it still would allow you to solve any initial value problem. Though what you would find is, since solutions of initial value problems of this kind of differential equation are certainly unique, your final answer for any given initial value problem would be the same no matter how you approached it for the general solution. Let's just spend a little bit of time here now thinking about the phase plane. There's our general solution. What will the phase plane look like? Well, the eigenvectors are going to generate what you might call eigenlines, more generally called eigenspaces. Those are going to be lines along which you get straight line solutions. For initial conditions on those lines, you'll get straight line solutions. Over here. Don't forget about your equilibrium point at the origin. Make sure you put a big dot for that equilibrium point at the origin. One line of straight line solutions is going to be along the vector 1, 1. If we place the base of that vector at the origin, this line right here with the slope of 1 is going to consist of straight line solutions. The eigenvalue is 9 positive, and so that means along this line, your straight line solutions are going away from the origin. as t increases. The other line of straight line solutions is along this vector when I put its base at the origin. Positive 4, negative 9. So I have to go down about a little over twice as far as I go over to the right. It would be around here somewhere. The slope would be negative 9/4 of this line. The eigenvalue there is negative 4, a negative number, so along that line your solutions are going to go in toward the origin. What about in between? Well, in between, the vector field, you can test this by using the CD-ROM or Mathematica. The vector field, for example, up here is going to be pointing, generally speaking, to the right. Up here it'll be pointing downward also because it'll be close to this straight line solution, which is going downward. Over here it'll be going upward because it's close to this one. So this is not necessarily exactly how the solution curves look, but it is the pattern of their general behavior. We might call this a qualitative picture of the way solutions look. Over here they'll do this. Over in the right they'll do this kind of thing. You can just think about the direction of the other arrows along the straight line solutions. And finally over here they'll do this kind of thing. And indeed, unless you lie exactly on this line with slope negative 9/4, you will tend toward one of these solutions that goes off either plus infinity in this direction, I guess I should say x and y go to plus infinity, or toward this solution where x and y both head toward minus infinity as t increases here. What's going to happen if you happen to be along the line through the origin with slope negative 9/4? For an initial value problem like that, what will happen is you will get the k2 equaling 0. And so you'll stay with this, k1 equaling 0. So your solution will look like that, and it'll stay on that line with slope negative 9/4 as t goes to infinity and go toward the origin, because this term will go away because the k1 is 0. So that's an example of a saddle point. If you want a more precise graph of it, of the phase plane, you usually need technology. Let's take a look at the technology right now. Zoom in on this. I'm going to go to matrix fields instead of HPG system solver. This is something you're going to want to get used to using. It's not completely flexible because the coefficients of the matrix, the numbers, the entries in the matrix, can't be just anything. You can modify them with sliders. A, for example, the upper left-hand corner of the matrix, can be anything between -3 and 3, same with B, C, and D. If you try to make it too big, like if I try to make that 5, it doesn't like it. Let's see. Yeah, it goes back to a default of the biggest number, 3. What I'm doing, though, to illustrate this particular system that I looked at is I'm multiplying all the entries in the matrix A by 1/10. Take a look at those entries. Zoom in on those. 5, 4, 9, and 0 were the original entries. I scaled them all down to be 0.5, 0.4, 0.9, and 0. In a sense, I scaled the matrix down by a factor of 1/10. Think about what's going to happen with the vector field. All the vectors in the vector field are going to get scaled down by a factor of 1/10. But they'll still point in the same directions. So the eigenvectors and the eigenlines that are generated, which you can see up here in the top left corner, are still going to be the same. The eigenvalues actually are not necessarily the same. They won't be the same. They will, well, maybe I better double check that. Certainly the vectors get scaled down themselves. Yeah, they won't be the same because those vectors are going to get scaled down. You're just looking at the direction field here anyway, not the true vector field, so these vectors don't have the right length. But the eigenvalues themselves are going to get scaled down also. Looks like, for example, if my starting point is on this line with slope -9 the red point is the position vector representing the point that I plug into the vector field, and the blue vector going backwards is the output of the vector field, A times V, and you can see it's not very long. It's, in fact, it looks like it probably is -0.4 times V, where V is the red vector. So it looks like one eigenvalue is -0.4, and in fact I can double check that by pressing this button that says eigenvalues. Yep, -0.4, they did get scaled down. And +0.9. If I now go over to this other eigenline, you can see that the blue vector now is almost as long as the red vector. It's 0.9 times the length of the red vector. So the eigenvectors stay the same. The location of straight line solution stays the same, but the eigenvalues change. I guess if we're going to get actual solutions coming into here, though, we have to go back and use HPG system solver. But you can see that the vectors in the vector field are following the same directions that I showed you up on the screen. And that's it for this talk.